Welcome to Module 6. We're going to be looking at refrigeration and then also briefly liquefaction in this unit. So the goals here will be that you can recognize the purpose of refrigeration and the Lindy liquefaction process, and then appreciate the role of each of those unit operations within the process. We want you to be able to propose designs for refrigeration and liquefaction processes so that you can meet given specifications and operate within the required constraints. And compare and evaluate your process design using coefficient of performance as a benchmark tool. And then finally, we want you to be able to select the appropriate refrigeration working fluid based on safe operation as well as the environmental and economic concerns. So just a review of what we've covered earlier on the refrigeration systems. The goal of a refrigerator is to transfer heat from a cold object into the surroundings, which are warmer. We measure that performance using a coefficient of performance, so sometimes people use COP, sometimes a beta, but in either case the goal is Q sub L, the heat transfer from the cold object, the low temperature object. The cost of doing this is the net work input. The maximum that this can be is determined based on the Carnot cycle, and it is TL over TH minus TL, where all of those temperatures are absolute. We sometimes choose to use the refrigeration system to heat something that's already hotter than the surroundings. So the goal of a heat pump would be to transfer heat to the hot whatever it is, surroundings, from the colder surroundings. So this might be you huddling behind your refrigerator, but it also can just be switching the airflows over your air conditioning units. Now a heat pump, the goal is high temperature heat transfer. The cost is still net work. The difference between this and the other is the goal, okay, the Q. Am I transferring heat from the cold object? It's a refrigerator. To the warm object? It's a heat pump. The maximum possible for a Carnot is going to be TH over TH minus TL. Now, if you play with the math, what you'll see is the difference between these two coefficients of performance will always be 1. And as a reminder, this is kind of our simple pictures of heat engines and refrigerators. Refrigerators require work input, take heat from the cold to the hot. So a vapor compression refrigeration cycle is typically what we do for most refrigeration systems. It's kind of like a reversed Rankine cycle, okay? The reverse of a turbine is a compressor. So I'm taking that gas and going from a low pressure to a high pressure. But it's going to still be a gas during all of that. The reverse of a boiler is a condenser. Right? I'm going to go from the gas to the liquid. The reverse of the condenser is an evaporator. It's like a boiler, but it's not going to require active boiling. Okay? You're not going to burn fuel, you're just going to do it in a heat exchanger essentially. Let some other fluid blow past it and it will do the evaporation more gently. And then the reverse of the pump. And this is where it becomes not like a reversed Rankine cycle. Because to reverse a pump would be a turbine but for liquids. I want to go from high to low pressure with a liquid. It is possible to build a liquid turbine, but the cost far outweighs what you will ever make from doing that. So instead, the cheap way of doing this is to put in an expansion valve. So the expansion valve is going to drop the pressure without any change in heat transfer and no work. So this is what the cycle might look like. So we're bringing it in as a liquid at a low pressure. We're going to evaporate it so it will still be at that low pressure and temperature, but now it's going to be a gas. I'll compress the gas to a high pressure. I'm going to then condense it so it's a liquid, but at that high pressure. run it through an expansion valve to drop the pressure back. So that will complete my cycle. So that first step there is reversible adiabatic compression. Actually, the numbering system is different, isn't it? Well, we'll just adjust anyway. So I go through a reversible adiabatic compression. If it's reversible and adiabatic, the entropy is the same. This is going to be all gas in the compressor, so therefore I can calculate the work by delta H. The heat transfer steps are always going to be Q equals delta H. Okay, so for the condenser, that's where the high temperature is happening. It's going to be H3 minus H2 for this numbering system, and it's all constant pressure. Then for the low temperature heat transfer, happens in the evaporator, that's going to be H1 minus H4 for this numbering system, and again the pressures are the same. Now our new piece of equipment is that valve. Okay, the valve with Q0 and if W0, and if there's no kinetic or potential energy change, then what we find is that it is isenthalpic. So H3 equals H4. And a drawing of this on a TS diagram is shown here. So 1 to 2 is an isentropic process. 3 to 4 is a virtually isentropic process. If you really believe that it's reversible and adiabatic, then it would be isentropic. But I'm not going to ever be able to reverse one of these valves. Okay? I'm not going to push it through the other way, and as it gets tortured, it suddenly gets its pressure back. That's never going to happen. So this is never reversible. So there's always a small entropy change across this expansion valve. So we'll look at an example. So we're using refrigerant 12 as the working fluid. The pressure in the evaporator is 400 kilopascals. The condenser is 1400 kilopascals. The refrigerant is going to exit the evaporator with 3 degrees of superheat. So what that means is I'm going to figure out what the saturation temperature is, and I'm going to heat it 3 degrees more than that. So if it came out to be 137, I would heat it to 140 degrees C. Okay? It's going to exit the condenser when it's cooled to a saturated liquid. I want to find the coefficient of performance for both the cooling mode and for the heating mode. So I use data out of Sontag, Borgnacki, and Van Wylen's thermodynamics textbook, but you can find equivalent data anywhere. So lots of different resources, many of them are available online. So the facts that I used to put this together, okay, so using this diagram here, P2 and P3 are going to be the same. This is the condenser, and so that's going to be the 1.4 megapascals or 1400 kilopascals. P1 and P4, these pressures are the same across the evaporator. That's 400 kilopascals or 0.4 megapascals. And then my temperatures, I know that it's going to exit the condenser as a saturated liquid. So exit of the condenser is right here. Okay, so it's going to be a saturated liquid there. And it's going to leave the evaporator with 3 degrees of superheat. So I'm going to find the saturation and add 3. Okay. Work is going to be performed in the compressor. I need to find those 2 delta H's, but I have this pressure and temperature defined awkwardly, but it's defined. And here I know the temperature, the pressure, and I will be able to finish all of this stuff up. Okay? Oh, and constant H at the expansion valve. Forgot that one. So here's the data that I obtained. This Excel file is available with the course notes in our learning management system. So you can look those up there and pause the video and really take some time to figure this out and make sure that you essentially agree with all of these values. And so what we find is that the work required for the compressor is 26.4 kilojoules per kilogram. And for that work, I will obtain 131 kilojoules per kilogram of heat input to the cycle, so heat from the cold temperature, and heat output from the cycle will be 157.5 kilojoules per kilogram. Okay, so the coefficient of performance in refrigerator mode is 4.97 or 5, and coefficient of performance in the heat pump mode is going to be 6. The difference between these is always 1. So what we're going to do is we're going to pause right here, and we're going to come back in the next video and talk about how we can tell, which fluid do I want to use. If you look in a textbook, you're going to see a wide array of data tables available to you. So we're going to talk about that in the next video.